Welcome, everyone. It's good to see that you're still here. A lot of your friends are working on the assignment, I think, but you're done, right? So things will become easier now, I hope. Well, they were already easy. I mean, this is all easy stuff, but I mean, they will become much more easier. Right, so today I want to continue this we've kind of talked about concurrency in the context of writing server applications. We want to look today at some of the issues around writing parallel programs on today's multi-core processors, what kind of options are available, try to understand a little bit what is this thing called hyperthreading, and what does it entail, the whole what are some of the issues across the entire compute stack, from user programs to all the way down to hardware? What are the problems with writing parallel programs and reasoning about parallel programs, speed ups compared to sequential program? How can you reason? What are you going to get out of your multi-core hardware, for instance? And we finish off with consistency models. All right. So exploiting parallel execution. So we use threads to deal with I/O delays in the sense that if we are hooked up to one thread, we don't want to just do that one thing. We want to deal with multiple clients at the same time. So we've seen this example of using threads in that context, but we can also use multiple threads, for instance, to speed up to solve a problem, any problem that involves a lot of processing faster by dividing up the work among multiple threads. Sort of if you're doing the labs this week, you have seen a Mickey Mouse example of summing up an array and how you can use multiple threads to do that. So I want to talk a little bit about the underlying hardware. Okay, so this is not something that I intended to do. So at a high level, any processor that you buy today is most likely a multi-core processor. Even your mobile phone has processors that have many cores. At a high level, what it means is each core has its own register file, its own set of physical registers, its own private cache hierarchy that it can use for storing the working set. And there is a shared cache that is used by all the cores. So we call each of these a core, and each core can run an independent process and a thread. And the different processes or the different cores have a coherent view of memory. It's not possible that if we do things properly, that a variable A has a value 10 here and a different value 5 here. And this is all enforced by the sort of this, there's a shared interconnect here that provides a communication mechanism between the cores. And so when they read and write variables that have a single copy in the virtual address space, they get a coherent view of memory. So you can already see that when you're writing parallel programs, if you're using a lot of shared variables, and if you have a lot of threads, and they're all trying to get a copy of the shared variable, there is going to be a lot of communication between the different cores. And to ensure that all of this remains coherent, and every processor core sees what the other core is reading or writing, at least writing to a shared variable, this all takes a lot of overhead. Okay. But we have mechanisms to ensure that. Okay. This multi-core processor can run multiple processes, where each process has its own virtual address space. So core 0 can run an independent process. Core B can run an independent process. And this is the predominant model in the cloud. In the cloud, where you have multiple users, they're all running independent processes, and each process has its private virtual address space. And if you do things properly, they should not be able to see each other's data or what the other processor is doing. It's not always the case. And we call this model multi-programming. So multi-programming is a very important use case of multi-core processors. Now, why am I saying that? Because the other use case, writing parallel programs, which today are written using multiple threads, so multi-threaded programming is hard. You can see with a simple example you have in the lab, you have so many options, so many different things you can do with shared variables. Solving bigger problems by writing very efficient parallel programs, multi-threaded programs, is hard, very hard. And you don't always get perfect speed up that you're looking for. So these are the two predominant uses of multi-core processors, server processors, and multi-programming, even without any parallel threads alone, is a very important use case for multi-core processors. Okay, so what's the deal with hyperthreading? Almost all processors today have. So this is a multi-core processor. This is one way to do multiple things, run multiple programs, multiple threads at the same time on a single processor. The other thing they do today is hyperthreading. In literature, it's also called simultaneous multithreading, or SMT. So when they sell you processors and they say, hey, you can buy this processor, it has 128 cores, they are really trying to sell you a combination of this. They're not really telling you that it's 128 independent cores. Now, to understand what I mean, we need to understand what hyperthreading is. Now, to explain hyperthreading is not, we cannot ignore some low-level details of how a processor looks like. Now, I want to spend 3 or 4 slides on something that I do for 12 weeks in my special topics computer architecture course. So let's see if we can get some intuition about processors, so we can understand hyperthreading and the difference between multi-core processes. So one way to build a processor is what we call an in-order processor. An in-order processor respects the, if you look at the assembly instructions, the intuitive model we have of how instructions execute is one instruction executes after the other. Everything happens in order. You take one instruction, you execute it. When you're done, you execute the next instruction, right? So an in-order processor respects the sequential programming model without any violation, all right? You can have a single cycle in-order processor or a pipelined in-order processor. A single cycle processor, one instruction takes one clock cycle. Only one instruction is executing at any given time, right? Now, we want to speed things up. We want to exploit some parallelism. Just like in real life, we want to do more things per unit of time. In one cycle, we want to execute as many instructions as we can. One way to do that is to use pipelining. So a processor is split into independent stages. A stage here is, so if you think about what steps are involved in executing an instruction. So you have to fetch the instruction. Instructions are typically stored in memory. You have to fetch the instruction. You have to decode what's the meaning of the instruction. What is it trying to do? Is it a memory access? Is it an add operation? You have to execute the instruction. And then you have to write the results back somewhere. And that somewhere is the register file. The registers where you maintain all the program state. So you can imagine that in a pipeline processor, in a single cycle processor, all of these stages is just one big thing. Everything happens in one cycle. There is no distinction between multiple stages. So in a pipeline processor, we build a processor with different stages, and we insert registers between the stages to store intermediate results of a specific stage. And this way we have some instructions in the fetch stage, some instruction in the decode stage, some instruction in the execute stage. This is poor man's parallelism. This is one way to exploit parallelism. And you can think of it like an assembly line at a car factory. So each car passes through many different stages, and each stage, in one stage you hook up the door, in another stage you do some paint and all that. In both these cases, in-order processors execute instructions sequentially. So I have an example here, actually. So this is how you do a sequential laundry. You don't have to understand the whole slide. This is a cartoon. So what are the steps in a laundry? You wash, dry, fold, hang. So if 3 students want to do laundry and you do sequential laundry, it looks like this, right? But you have independent resources here. You have a washer, you have a dryer. So what you can do is you can do pipeline laundry, right? Once one student is done with the washer, the other student can use it, right? And at some point, if you look at a vertical slice, all stages are doing something, right? Someone is doing what is Alice doing? I don't know. someone is washing, someone is folding, someone is, as long as you can independently divide the work in such a way that there are multiple, that you can use these machines independently, right? So if you have a separate washer, separate dryer, whatever. So this is an example of how they do pipelining in a process. The one thing they realize over time, yeah, you don't have to do things in order. So programs are written and translated. So if you look at assembly instructions, they all look, instructions are placed next to each other and you execute one instruction after the other, but there's really no reason to execute instructions one after the other. So for instance, this is whatever ISA is that, I don't know. So here are my 3 instructions that I just wrote. So if we stick by the sequential programming model, if we respect the sequential programming model, we will execute I1. Once we are done with I1, we will execute I2 and then I3. But the question is, the real question is, do we need to wait for I1 to complete before we execute I2? Do we? We do. That's a constraint. Let's call it read after write dependency. So I want to read R1 after it's written by I1. Otherwise, my program won't be correct, right? So here I need to conform to the sequential model. But do I need to wait for I1 and I2 to complete before I execute I3? No. So this is something they exploit in out-of-order processors. Out-of-order processors execute independent streams of instructions in parallel. They have the machinery, which is very complex, to identify instruction streams that depend on each other, where there are dependencies, and instruction streams where there are no dependencies. So an out-of-order processor will take these instructions and do some quick analysis to figure out, build a graph like this. Okay? It will put I1 and I2 somewhere in a buffer. It will put I3 somewhere, and it will tell the functional units, ALUs, arithmetic logic units, whatever, hey, here are the dependencies. You can execute I3 whenever you want, and execute I1 whenever you want, but don't execute I2 before I1. By telling this, by having this machinery that can tease apart these dependencies, and the property that the only dependency you care is read after write, such as in the example shown above, you can exploit a lot of parallelism by doing things out of order. And this is the intuition behind out-of-order processing. Now, why do they do this? The problem is, if instruction I1, memory accesses are slow. You know this from 2300, 100 cycles. If we execute instructions one after the other, I2 is stuck for 100 cycles. That's okay. This is part of this is what the programmer is saying. I want I2 to execute after I1. I2 is a consumer, I1 is a producer. But the programmer is not saying I3 should wait for I1. It doesn't say this anywhere in the program. So for 100 cycles, the processor will be stuck And so what out of order processor will do, it will execute I3. It will execute I4, I5, or any independent instructions that don't depend on the result of the load instruction. It will go fetch them and execute them while the memory access is being resolved. So the key idea behind an out of order processor is to hide or tolerate the high latency of memory accesses. And the line here, the sentence is, keep doing useful work if one instruction is stalled on memory. If one instruction is stalled, don't stop doing work. There is a lot of independent work available. Okay, go figure it out. And so a single cycle CPU at a very high level, I want to go through it very quickly, and this will not be on the exam. You fetch an instruction from memory, you have a program counter, you decode the instruction. What is the instruction saying? Which register does it want to write? Which register does it want to read? You get the values from the register file, which is hooked up to the this logic here. You compute the result. For instance, you do an add, or you do a memory operation, and you write the results back into this register file. The register file contains what we call the architectural state of the program. This is the only state the programmer cares about. Everything else, all the other logic, ALU, whatever, is just to execute instructions. If there is an interrupt or if something happens, the only state the programmer cares about is what are the contents of the register file. This is all we care about. This is all that is exposed to the software, the registers. So pipelining in out of order processors try to exploit what is called instruction level parallelism, or ILP. This is very important. So you want to execute more and more instructions in parallel. So an important thing to remember is that ILP is a property of the program. If the program does not expose ILP, if every instruction depends on some prior instruction, then an out of order processor cannot do anything. If you give me a program that has a graph like this, and so on, there is nothing an out of order processor can do. You're basically just stuck executing things one after the other. But it turns out that real programs expose a lot of instruction level parallelism. Their graphs don't look like this. They're more like, in the extreme case, you have instruction chains, there are dependencies, but there is a lot of parallelism. So here, an out of order processor can execute I1, I2, I3, I4 in one cycle. Read after write dependencies or raw dependencies inhibit parallelism. They mean that one instruction must finish before the next one can begin. And if there are no raw dependencies, there is an opportunity to exploit ILP in hardware. All right, so this is just a pipelining example. So what they do in pipelining is they actually insert these registers between the different stages, just like if you put a basket here, between the dryer and the folding, whoever is folding, you need some buffer to store all the clothes you get out of the dryer. So they have these registers between the stages to store the intermediate contents. So each cycle, instructions stream through the pipeline, and at any given point, if you look at the vertical cut through this diagram, where instructions are executing here, and this is time, you can see that a lot of instructions are in the pipeline at any given point. Okay. So these registers are not exposed to software. These are what we call non-architectural state or non-architectural register. There is a problem here. This is a fetch stage. So what if there's a branch instruction in this stage? What is the problem with the branch instruction? Why is the branch instruction different from? So each cycle, I'm fetching the next instruction, and instructions are marching through this pipeline, just like, cars in an assembly factory. But when there's a branch instruction, what is the problem? You don't know what the next instruction, which next instruction you want to fetch from memory, right? It could be the next instruction, or it could be the instruction at the target, right? So what they have here is something called branch prediction to predict the outcome of the branch and to predict where the CPU should execute the instructions. And they use neural networks or recent history for that particular branch to predict the outcome of the branch, so they can keep doing useful work. And if they're wrong, there is machinery to recover from the misprediction. Okay. So the key idea of out-of-order processor is that a stalled instruction does not inhibit the execution of younger independent instructions. The key components of an out-of-order processor, so you fetch instructions in order. So there's a front end of an out-of-order processor which fetches instructions from memory in program order. You don't want to fetch instructions out of order. There is dynamic scheduling hardware in the middle of the processor that execute instructions out of order, respecting the dependencies between instructions. So the key piece of the machinery that enables out-of-order execution is a dynamic scheduler that figures out all the dependencies and sends independent instructions to the execution units. And everything retires. Retirement means you do all the checks. When an instruction is done, finished, before you write its results to the register file, you make sure there are no exceptions, no faults, nothing, no branch misprediction. This instruction really should write its results to memory or register file. So an out-of-order processor that executes n instructions where n is greater than 1 is called a superscalar processor. So all the processors you have today, even in your mobile, even in your laptops, are most likely superscalar processor. You fetch 4 instructions from memory, you execute 4 instructions, or at least you try to execute 4 instructions. Now, if you give me a program like the example I just showed you, where there is just one long dependent chain of instructions, a superscalar processor cannot help. But that's not typically the case. And we say that a superscalar processor has n issue slots to fill each cycle, meaning it has n functional units. These functional units could be arithmetic logic units, multiply, accumulate, whatever. So at a high level, superscalar processor can execute n instructions each cycle. And we say that each cycle, it tries to fill n issue slots. If there is no instruction level parallelism, if we are waiting for memory, all issue slots can go empty. Okay, so we're going to move to hyperthreading now. Okay, so this is our out-of-order processor. Everything I said, this is a high-level diagram. So you have many of these functional units, right? You have many of these functional units. This is like the issue slots that I talked about. And you're trying to, and this is the operation queue. where the dynamic scheduler is putting all the instructions, hey, go and execute these instructions, they're independent. And you're trying to fill these, you're trying to grab operations from the operation queue or instruction queue or issue queue and trying to keep all the functional units busy every cycle. Every cycle you are trying to issue n, because that is your capacity, you're trying to issue n instructions to these functional units. Now, what I'm trying to say, what I was trying to say was that you cannot always do that because of dependencies. It's a very hard problem. What should n be? So n is typically 4 up to 8. You could end up with a program where you are working on below your maximum capacity, where a lot of issue slots are just going empty every cycle. Okay. So what is hyper-threading or simultaneous multi-threading? So what they try to do is, so they have multiple. So the problem is right here, right? So let's say you have an n of 4 here, and you could be working below your capacity if there is not enough ILP. In one cycle, you could probably issue only 1 instruction. In the next cycle, 2 instructions. So a lot of issue slots are going empty. So what they do is they replicate some of these structures here. So there's a second register file, there's a second operation queue or instruction queue, and there is a second program counter register. And they try to fill these slots using operations or instructions from multiple threads. Okay. So now this processor is trying to fill these n issue slots, not from one thread context, but from multiple thread contexts. So if one thread is stuck, or if one thread does not have enough ILP, probably the other thread has instructions that can be executed in that cycle. So now we have thread A here and thread B here. And they're both trying to sort of fill the issue slots, all the issue slots. So the way it looks, okay, this diagram probably. So I want to start. So on the horizontal axis are the issue slots. So let's say there are 4 issue slots. In each cycle, you can execute 4 instructions. And this is your classical superscalar out-of-order processor. It can only execute 1 thread. So here we have 5 threads, but the superscalar processor is only executing 1 thread at a time. So in this axis are cycles or time, and in this axis are the issue slots. So you see that some cycles, the superscalar processor cannot do anything because of dependencies or because of memory accesses. There are some cycles where all issue slots are going empty. There are other cycles where only 2 slots are full. So it's working at 50% capacity in the first cycle. And the problem is we don't have enough ILP if we only execute instructions from a single thread, right? So this is pretty bad. We have this out-of-order processor, we paid for it, it has a lot of machinery inside to execute n instructions in one cycle, but our application doesn't have enough ILP. So the other option is fine-grained multi-threading. So what you do is each cycle, you interleave, each cycle you execute instructions from a different context, right? And the idea is, if one thread doesn't have any work, probably the other threads have useful work to do. Now, you can do this sort of fine-grained multi-threading. The kernel can do that using timer interrupts and all the mechanisms that we discussed. Or there could be a context switching circuitry in the hardware itself. The hardware can do the context switch. But the key idea is, each cycle you execute instructions, you try to fill the issue slots from a different thread or from a different context. So here we have what we call, in this case, we have horizontal waste and vertical waste. Okay, horizontal waste because there are cycles where I don't have enough work. I can only fill 2 issue slots. There is vertical waste because there are cycles where I don't have anything to do. And fine-grained multi-threading using help from the kernel or from the scheduler in the hardware, it tries to do something about it. But there are still a lot of empty slots here, right? There are still a lot of empty slots. There are not on the vertical axis, but there are still empty slots on the horizontal axis. Okay, so in fact, how this plays out in reality is really depends on how much work the threads have. So if you look at the color scheme here, this is just one thread, T1. This is thread 1, and the next cycle, thread 2, next cycle, thread 3, next cycle, a different thread, and the idea is that if one thread is stuck, perhaps the other threads have some work to do. Let's try that and try to fill all the issue slots. Now, with simultaneous multi-threading or hyper-threading, in each cycle, you're trying to fill all the issue slots by taking instructions from 2 different threads. So this is, in this cycle here, you have this instruction from T1, this is from T1, this is from T2, right? You're trying to you're trying to keep all the functional units busy. You're trying to fill all the issue slots by taking instructions from multiple threads. So here you have thread 2, thread 3, thread 4, and then probably for some reason there is nothing to do. There is no way to fill the issues. So they have heuristics and they have mechanisms built into the processor itself to get independent instructions from different thread contexts and try to fill all the issue slots. So this is hyper-threading or simultaneous multi-threading. Okay. Are there any questions about simultaneous multi-threading or hyper-threading? Well, the high-level idea is pretty simple. You're trying to exploit as much ILP as you can, and you're trying to do it by taking instructions from 2 different or multiple threads. So if you limit yourself to, so this would be a 2-way SMT, or what Intel likes to call hyper-threading. But IBM has processors with 8-way SMT. I'm not sure if they have more than that. Okay, so what was I going to say? So hyper-threading, I mean, is trying to do what the superscalar processor and the fine-grained multi-threading is trying to do at the same time. It's trying to exploit ILP just like superscalar, and it's trying to exploit So if one thread has a long latency operation, it's waiting for memory, probably the other thread has some useful work that could be scheduled on the functional units. So we already talked about multi-programming and multi-threading. So if you ever, you're curious, if you pay for an expensive processor, if you ever do cat proc CPU info, or if you do top, most operating systems will actually expose hyper-threading as separate cores, which is not really true. So they will show you that if you do cat is to print the contents of a file, if you look inside proc CPU info, you can see all the cores that are in your system, and you will see 32 or 64 cores, or 16 or 8. But if you look carefully, you realize that they are hyper-threaded cores. So each core is really just a hyper-threaded core, which is not perfect replication or an independent core. It's really just two hyper-threads inside a core. So let's see if so we have an 8-core system. Each core is two-way hyper-threaded. So this means we have 16, let's say 16 hyper-threaded cores or 16 cores. And we have a processor with these specs. And we want to write a parallel program to do the sum of n integers. And each thread will do a partial sum, and we will get the result. And we want to write parallel programs, and we want to see what kind of speed up do we get. Okay, so we have a global variable here. So now you have some intuition about what a multi-core processor is, what a hyper-threaded processor, what is hyper-threading. So here we have a global sum, a variable global sum. And we divide the work evenly among threads. And we have a mutex. And so what we're trying to do here in our first attempt to write a parallel program to speed up parallel summation, what we're going to do is each thread is going to grab a mutex on this critical section, and it's going to update the global sum variable in a for loop. So each thread gets a slice of the work, right? So this thread has a starting index. So let's say thread 1 is probably doing sum from 0 to 12, and thread 2 is doing from 13 to 20. And so this is how we're doing the work division here. So in a for loop, start to end, grab the mutex and add I to the global variable. Okay, so this is, each thread is doing that. Okay, so this is one way to do that. So we have a global variable in which we are keeping the final sum, and each thread will do its share of the work in this for loop. So what do you expect will happen in terms of as you add more cores, will you see a lot of speed up? Is this the best way to do parallel sum? Is this the best parallel program? Probably not. So if we look at the results, it's horrible. 50 seconds or so on a single core, and it goes up to 456 seconds with 2 cores, and it keeps going up, and there is some anomaly here at 8 cores, and then hyper-threading, this is hyper-threading from going from 8 to 16. It doesn't really help. So why is that? Why is this? Why is a parallel program should be faster than a sequential program, right? So this is a sequential program, one thread, and I'm throwing more resources and I'm getting slower. So parallel programming is not easy. First of all, the cost of P and V operations is very high. And so what we are doing here is we have one global variable. And if you recall that picture of a multi-core processor with caches, and I told you that there is an interconnect and there are mechanisms so that each core gets a consistent view of a shared variable. So you can imagine that this global sum variable is just ping-ponging between, it's just every core is saying, hey, give me the global one, give me the latest value of global sum, and then it's writing, and then every core sees the new value. And this has a lot of cost. And then there is the cost of these P and V operations are not cheap. You actually have to go inside the kernel. You have to enforce the kernel to stay out of that specific trajectory that we saw in the previous lecture. This is not just a user level function with small overhead. This is very high overhead. Okay. So we have a global variable, which is really just a terrible idea. Cores are just hammering upon this variable, and it's going from one core to the next and getting evicted from the cache and all that. All right, so what can we do? So let's do something different. Let's have a psum array, and each thread updates a specific writes to a specific location in the array the sum that it computes. Okay, so now we have, so because the array is like depending on how many threads we have, each thread gets to write at a specific location, and the index depends upon the thread's ID. So now each thread does the sum and writes its sum to a specific location in the sum array. So now we get rid of the mutex operations, right? Now we don't need any synchronization, because two threads will not write to the same index at the same index in the array. So what do we expect now? Do we expect better outcome? Possibly, right? And so this is what we get. We get orders of magnitude faster than the mutex. So in your lab this week, think about this. Think about this. But actually, we're not doing any measurements, but still. And the hyperthreading helps a little bit as well. So you go from here 5 seconds to less than a second. Okay. Can anyone tell me if we can do better than that? What is the problem here? So remember, what is the cache line? You need revision, yeah? Your exam is coming. So a cache line is typically 64 bytes or so. So this array will probably fill up an entire cache line. So you're still writing to the cache, you're still writing to memory. Probably those writes are still being made visible to other cores. There is some work in that. You're reading from other cores. So what can you do to make it better? Yeah, all right, good. So if we create a private variable and try to do it like this, so now this sum variable will be stored in the local register of each core, right? Each core has a local register file. And if we create, and actually, wait a second. This will probably go to the stack first and then probably on the register file. Yeah, it will be in the register. And then we can do the sum. We can store the sum to this local variable, right? So this will end up in a register. The compiler will make sure, because this is a frequently used variable, it will end up in a register. So anything in the register, you know that it's way faster than memory. You know this, right? So accessing register file is faster than memory. So now we only do one final write to memory or to the cache line, and we accumulate the sum in a local variable. Okay. And if we do that, we see speed up. Sorry, we see reduction in execution time. And at some point, because this is we don't have enough work to do, more cores are not really helping. Okay. So you can see that writing, this is a very simple example. This is an embarrassingly parallel problem. There are not many difficult to reason about, dependencies that are difficult to reason about. Work division is really simple. And even with a simple program, you can write a version which is horrible, and a version that is somewhere in the middle, and then a version that is really, really fast. Okay. So this is what I wanted to convey. And so this here is actually hyperthreading. And so now hyperthreading is actually not really helping at all. So whether or not hyperthreading is useful remains a contentious issue. But it's a good feature to sell processes, right? It shows as anything that helps you sell processes is okay. Okay, so we have seen this was our this is all the parallel programming we will do in this course. We don't have more time. So I want to continue. So how much time do we have? Do we start it? Oh, we have time. Okay. So let's see how we characterize the performance of a parallel program. So speed up is really simple. So if we have P processor cores and TK is a runtime using K cores, so speed up is T1 over TP. Now T1 is, you can take a parallel program and run it with one thread, or you can take the best, most optimized sequential version of the program and run it with one thread. Now, what's the difference? Why is there a difference? What's the problem with just using a parallel version and running it with one thread? Parallel version has P and V operations. We still have to pay for these operations. So when we take, there are two types of speedups: relative speedup and absolute speedup. We call relative speedup when T1 is the running time of the parallel version. It's relative to the parallel version. And we say absolute speedup when we find the best sequential version of the program with no P and V operations, nothing, right? So this is how we quantify the speedup of parallel programs. And efficiency is kind of interesting. Speedup alone tells you something, but it doesn't tell you a lot. So with efficiency, you divide the speedup by P, and you get a number between 0 and 100. So this tells you how efficient you are. How efficiently are you using the multiple cores for your programs? So let's say T1 is 100 seconds and TP is 20 seconds. And P is, you're using, let's say, 10 cores. So what's the efficiency here? So 100 divided by 10 multiplied by 20. So 20, 25, 2. So sorry, I'm slow. So that's about, I need a computer to solve this. So the efficiency here is 50%, right? So this is more, this is one way to reason about. You're working at 50% capacity, or 50% is your efficiency, right? And the speed up here is 5x. So 5x, if you tell someone I'm getting a 5x speed up, they'll be like, okay, But if you have 50% efficiency, okay, where's the other 50%? What's going on with the other 50%? So it's something to reason about more easily. So here's the efficiency of our p-sum local. Up to 75%, in my experience, is you are a rock star. Parallel programming is really hard. If you can get 75%, that's really good. But our example is also easily parallelizable. So there is actually a interesting law, Amdahl's law, that quantifies what is the maximum speed up you can get out of a parallel program. Okay, so it's really very simple. So let's say t is the total sequential time required, and p is the fraction of time that can be sped up. Okay, so this p is different. Okay. So whenever you take an algorithm, sorting, searching, your favorite algorithm, there is a fraction of work that you can do in parallel, where you can throw multiple cores, and there is a fraction of work which is sequential. An example in your concurrent servers is, I don't know. So all the work you do at the beginning to set up all the connections and create all the data structures, all the arrays, you cannot do that in parallel. But once client starts coming, you can use multiple threads to speed up that. So there's a fraction of total time that you can speed up. Let's call it P. So Amdahl's law really says the speed up you are going to get is bottlenecked by the portion that you cannot speed up. Okay. Or when you use multiple resources, multiple cores, you're only going to speed up the portion that is parallelizable, and the rest will remain unchanged. It's really that simple. So if P is the fraction of time that you can parallelize or speed up using K processors, that becomes P dot T over K, and the remaining time stays the same. So 1 minus P multiplied by total sequential time stays the same. Okay, it's really very simple. Now, let's say you throw infinite cores at a problem. You have a problem, and you want to use parallelism, and you throw infinite resources, infinite cores. So help me solve this equation. P dot T over infinity plus 1 minus P dot T. What do I get? So this goes away, and you're still stuck with that, right? The implications of this simple, high school math are interesting. So let's do an example. Let's say I have sequential time of a problem is 100 seconds. And P is 90%. Pretty good, right? 90% of the portion of the time, 90% of the work, you can easily parallelize. Remaining 10%, what is the maximum speed up you can get? If P is 90%, what is the maximum speed up you can get? So 0.9 multiplied by 100 over, what is K? This should be 10. Okay, I have an example here. So, sorry, I'm not good with that. So the total time required is 10. This is a fraction of time that you can speed up. This is just, sorry, this is the speed up factor. This is not. So what you get is 2. And the least possible running time is 1. So the best speed up you can get is 10. You don't have to do any math. It's really very simple. If you make this thing 0, so 10 times. So even if you throw whatever number of processes on this problem, you are bottlenecked by the sequential. This is called the sequential bottleneck. So this becomes your bottleneck, and okay. So one implication of Amdahl's law is that we still need faster single thread performance. We still need faster cores. We need more cores for sure to exploit parallelism. But because there are sequential bottlenecks in real applications, we still need to figure out a way to build individual cores faster, right? Because the sequential bottleneck is always going to hurt us. All right, the last issue that I want to discuss today, and then I'll let you go, is so this is a problem. Let's think about this. Memory consistency. The issue is when you have concurrent threads running on processors, different processors, there is this problem of instruction interleaving. Okay, so let's do it through an example. So the initial values are, the initial value of A is 1 and B is 100. And so thread 1 writes, assigns 2 to A and then prints B, okay? And thread 2 writes something to B and prints A, okay? So thread 2 is trying to print WB and thread A is trying to print WA. So when you print something, you need to read, right? So we call it a read. So there's a write operation in each thread, there's a read operation, and then that's happening in both threads. So the question is, when you run this program on a multi-core processor, what are the possible outcomes, right? What are the possible outcomes? Now, and the way this is handled is by specifying the memory consistency model, right? So the classical model is, the most restrictive model is sequential consistency. And sequential consistency means that as long as we should respect we should not violate the ordering of instructions within a single thread. So this order for thread A, thread 1, and this is the order for thread B. We should not violate this order. Otherwise, there could be an arbitrary interleaving of instructions from multiple threads, okay? Now you can imagine that the out-of-order processor is trying to execute things out of order. It's trying to execute a lot of instructions every cycle. And the question is, when one thread writes, when should we make its value visible to the other thread? Okay, we don't want to go that far in this course, but let's try to at least reason about the possible correct outcomes under sequential consistency. Okay, so the way we do this is, so these are our constraints within a single thread. Okay, we must not violate these constraints. And other than that, there could be arbitrary interleaving of instructions from the two threads. So that leaves us with a few possible outcomes. So imagine that this instruction, we have no clue when you run this program on a real processor, all bets are off. We have no clue what will happen, what we will get. But as a programmer, we need to give the programmer certain guarantees, certain outcomes that are possible, and we need to tell the programmer, you will never encounter these outcomes. And the way we do that is by specifying the memory consistency model. So let's say this write happens first. The only two options, so I want to respect this. I don't want to violate the constraints on the top right of the slide. I don't want to violate. If I don't want to violate those constraints, I have two options. I can execute this instruction, or I can execute this instruction, right? So then I have RB and WB, and after RB, I could execute, I can only execute WB and RA. And that gives me 102. So 100 is what, blue is what thread 1 is printing, and red is what thread 2 is printing, right? So you get, if you do this for all the possible outcomes, combinations of, possible interleavings, you see that what are the impossible outcomes? So here you get 102. What does it mean? That it means that if thread 1 prints 100, what does it mean? Then it must have executed the write. And because it's easy to see here. So this write happens before the read of A. So this is 2, and this is, sorry, this is, these outcomes are impossible because in order to reach these outcomes, RA and RB needs to happen before WA and WB. It's as simple, it's very simple. And that means you violate these constraints here. Okay, so the only outcomes that are possible without violating those constraints are the 6 outcomes that are shown. So I still want to pick one and okay. So this read is after this write, so we get 2. And this write and this read is before this write, so we get a 100. So this is this looks simple, right? This looks simple to deliver, to build hardware that delivers these outcomes. It's really intuitive and simple, right? You can't you can, as long as you don't violate these constraints, you get these outcomes. So let's see an example where you can build hardware that looks well-performing and correct, but which can deliver these impossible outcomes. So imagine we have write-back caches. So anyone remembers what a write-back cache is? Okay, I need to do revision lectures. So write-back cache is where whenever there's an update in the cache, you don't write the result through to memory. You wait for a replacement or an eviction. So you write back the cache line to memory only on eviction, right? So imagine you have a write-back cache, and there's no coordination between the two cores, right? Core 1 and core 2, there is no coordination between them. So thread 1 on this core writes to its local register, sorry, to its local cache. It assigns 2 to A. Okay. So this thing happens. And then the second thread writes 200 to B, right? So this, so far so good. So now there is no coordination between the two, and read of A gets the result from memory and prints 1, and read of B gets the results from memory and prints 100, right? So if there's no coordination between caches, we don't have sequential consistency in this case. So if someone tries to sell you this processor, which does not have coordination between cores, and you run this program, you won't have sequential consistency. So you will get this output, 1 and 100, and you have no clue what is going on. So how do we solve this problem? So there is something else called Snoopy coherence, Snoopy caches. So what we do is we associate a tag, which is basically a state, with each cache block: invalid, shared, exclusive. So before a core can write to a cache line, it needs to acquire exclusive access to that line. Okay, so what does it mean? So when it does a write to A, it now has the exclusive copy of A. Okay. Now, if thread 2, so similarly, thread 2, core 2 has exclusive copy of B. So now thread 2 wants A. So what they do is they send this request over an interconnect, and when core 1 sees that, hey, I have the exclusive copy of this variable and someone needs it, it stops the memory from providing the stale value, and it supplies the value from its local cache. Okay, so now core 2 sees the most up-to-date value, and so it's called Snoopy coherence because you are snooping on the caches of other cores. So you're snooping the whatever is stored there. Same is true for B. And now the two lines are in shared state. Okay. Now the two lines are in shared state because they are being shared by the two cores. No one has an exclusive copy of A or B, and to write again to A or B, they will need an exclusive copy. So if you have Snoopy cache coherence, then you get sequential consistency. Now the problem is sequential consistency. It puts a lot of constraints on your out of order processor. You cannot do any buffering. These operations are really expensive. Before you want to do a write, if you have to tell to today's processors have 200 cores, more than 200 cores. So these wires for enabling, providing Snoopy coherence are really, really long. And these are multi-cycle operations. So if a processor has to wait after every write for, I don't know, 20 cycles, so everyone is aware that there has been a write to a shared variable, that is a real problem. So this is a very restrictive model. What they use in reality is something we won't do here, relaxed consistency, where they relax some of the constraints in this that we have seen here. So they let the processor execute a read or a write, even if an earlier read or write from a different processor is not yet visible to the processor. Okay, so what I want you to be able to reason about is sequential consistency. Okay, that is important. So what could happen? So I'm going to give you a flavor of the kind of things we can ask you in the exam. Let's say at some point, this is the initial state of the variables, and I say b equals 1. And at some point, I have these instructions. Okay, under sequential consistency, can you have the following outcome where both are not taken? Okay. Huh? All right. So I'm just giving you an example of the kind of things we could ask you. So if this one is taken, I think this is more interesting. Is this more interesting? So now if this is taken, you can reason about this one, that this may or may not be taken, but there couldn't be a scenario where both are not taken, right? Okay, so I don't have more. I'm sorry. All right, so that's it. Some issues in concurrency. This is the last lecture on concurrency. There's one more lecture on linking on Thursday, and that's it. We're done. I leave it to you what you want to do in week 12. I don't know. What do you want to do in week 12? Huh? Well, there are two possible outcomes of that. It could scare you a lot, or it could prepare you. I don't know. Which one should I do? Okay, so this is a very important course for your future. A lot of the systems courses that you're going to take, this will be the foundation. You really have to revise all the content until Thursday. Oh, okay. So I will do that. I will do. Is there a specific topic that you want me to do, or just bring problems, or do a lecture? What about virtual memory? You know, I used to teach recursion to first-year students, and now I'm realizing that that was probably easier. Yeah, people are very active on Ed. Yeah, yeah, okay, I can do that. All right, so you want exam questions. You don't want to keep gaining new knowledge. All right. I'll bring exam questions. The problem sets that you will see on the website and the problem sets that I will show you in week 12, exam questions will be of the same difficulty. There won't be any surprises.